Hey everyone, welcome back. So today we will be discussing about multiple linear regression. Already we have discussed about simple linear regression where it contains only one feature and a target. In multiple linear regression, there are multiple features and multiple targets. Okay, so let's recall something. What is mean by regression? Okay, what is mean by regression? It is nothing but predicting the continuous variables. Okay, predicting predicting continuous variables. Okay, all right. So how it is differ from simple linear regression? Okay, so the only difference is it contains many features, more than one feature. Okay, so let us take one example. Okay, so the example we have discussed that let us suppose we are calculating the price of an house. Okay, so the features it will be depending on the parameters. It will be depending on our area. Okay, the number of bedrooms. Okay, bedrooms and number of rooms. Okay, and many more, and this indicates the cost. Okay, these three factors will be dependent on cost. Okay, will affect the cost. Okay, so how we can represent it? Okay, so let us suppose you have a this is it contains three features, right? So it is a three-dimensional data. So okay, this is area, this is bedrooms, number of rooms. Okay, the data will be like this. Okay, then here we will be drawing a plane, the optimal plane. Okay, a optimal plane, a regression plane. Okay, optimal plane where the absolute error will be least. Okay, so the formulation of a plane is represented as y equal to a plus bx. Okay, bx1 plus cx2 and so on, right? So in machine learning terms, let us introduce some other. So for better understanding, let us assume that y is equal to, okay, in place of a, b and c, let's indicate it as beta naught, beta 1 and beta 2. Okay, so it is represented as beta naught plus beta 1 x1 plus beta 2 x2. Okay, beta 2 x2 and so on. Okay, so it is accumulated as y equals to y equal to summation I equal to 1 to n beta I xi, okay, plus beta naught. So this is represented as y. Okay, this is the formula of multiple linear regression. Okay, so we can write it as y is equal to beta 1 into area, okay, plus beta 2 into rooms. 1 minute. Okay, beta 2 into rooms and etc. So on. Okay, so these beta 1, beta 2, okay, 1 minute. So beta 1, beta 2 and beta 3 and more, these are known as weights. So I have given an example for the weights in the previous video, that it is also known as how much y is dependent on x, how much weight it is dependent on x, and beta naught is an offset, so it is a constant. Okay, I have also given why beta naught, I mean c is used in previous video. I have used it as c. So why c is used, and with an example I have given the idea. So please check out the previous video so you can get a knowledge on how simple linear regression works. Okay, So we can write it, so this is the formula. Okay, so we can write it as y equal to y cap equal to okay, beta naught plus beta 1 x plus beta 2 x2 beta, so y cap means only one. Okay, only one plane. So x plus beta 3 x 1 2 3, okay, and so on 3 and so on. Okay, so we can represent it in the vector form, right? So here if we draw like this, y1 cap plus y2 and so on up to y100, let us yn, okay, yn, okay, we can write it as beta naught and so on up to beta naught. Okay, so here the constants, the weights won't change, but the x and y values change, right? So after we finding the optimal weights, normalized weights, the x and y values changes, but weights don't change, right? So here the weights are similar, but the coordinates will be changing. So here we will be writing beta 1 x11, okay, next beta 2 x12 and so on. So here beta 1 x21, so on, beta 1 xn1 and so on. Okay, so we can take out the beta 1 beta 2 beta 3 outside, right? Using, so this is entirely based on matrices. So I hope you have a basic idea on the matrices. Okay, so this is converted into okay, this is converted into beta naught, beta naught, beta 1, beta 2 and beta 2 and so on up to beta m. Okay, beta n into 1 1 and so on, 1 into x11 x12 and so on up to x1 m n. Okay, here x21 x22 and so on up to, okay, so this is we have taken out the every weights into a vector. So this is a basic transformation in the matrices. Okay, so we have represented it, this table as, we have represented it as this. Okay, so we can write it as y cap, okay, we can write it as y cap equal to x beta. Okay, we can write it as, right, this is x matrices, this matrix, okay, beta is this matrix, y is the entire matrix multiplication. So we know that the error we have discussed, error equal to y minus y cap, right? So y is the current point, this is the optimal point. Okay, we need to find the optimal, this is optimal point, this is the current point. Okay, right? So the error is measured like this. So we can write it as E equal to, so in the matrices form we can write error equal to x1 minus x1 cap, x2 minus x2 cap and so on up to xn minus xn cap. Okay, understood, right? So the cumulative of all the difference, all the errors at the each point, so we can write it as the entire E equal to, you know that E equal to summation of 1 to n xi minus x cap whole square, right? So this is E. Okay, now it is represented as E1 plus E2 plus E1 square plus E2 square plus E3 square and so on, right? So in matrices, the entire cumulative is represented as E transpose E. Okay, this is a property of matrices. So we can write E equal to E matrix E transpose E. Okay. From here we will be deriving the entire multiple linear regression. Okay, it is very simple. The similar thing we have done in the simple linear regression, that is differentiating and equal and differentiation of E equal to 0. We will be doing the same thing here, but in the matrices. So I hope you have just a basic knowledge on the matrix. So I just want to explain you the mathematics behind this. That's it. Okay. Okay. So now let us start. So E is represented here. So E equal to E transpose E. Okay. All right. So it is represented as Y minus Y cap transpose into Y minus Y cap. All right. Okay. So now we know Y cap is known as X into B, right? X into beta. So let's substitute that. So it is known as Y transpose minus X beta transpose into X minus X beta, Y minus X beta. Okay. So this is the simplified thing. So let's multiply both the things. Okay. So now it is represented as Y transpose into Y. Okay. Minus Y transpose into X beta. Okay. And then XB whole transpose into Y plus, okay, X beta whole transpose into X beta. All right. Okay. In the matrices, this thing, okay, 1 minute. So in matrices, 1 minute. Okay. So in matrices, this thing and this thing is similar. Okay. That is A transpose B. Okay, A transpose B equal to B transpose A. Okay, we'll be using this formula here. So it is represented as Y minus, okay, minus 2Y Y transpose X beta plus beta transpose X beta. Okay, so this is E. Now this is E. We need to differentiate it. Okay, all right. So we got the E. Now we should differentiate it and differentiate it according to the weights, right? The weights must be the beta must be optimal. So if this optimal, then with this the error must be 0. So we need to do E differentiate E beta equal to 0. Okay, we need to differentiate this whole thing into equal to and equate it to 0. Okay, so we will be doing the same thing. So differentiating it, so with respect to beta it becomes 0. Okay, with respect to this, the, okay, let's set is 0 minus, with respect to this, the equation becomes 2 into Y transpose X. Okay, so now we need to differentiate it. Here we can differentiate it. So the problem here is it has beta transpose. Okay, and here beta, if it contains only beta, then we have done the same thing like here, but here the beta transpose is there. So in some, like in mathematical terms, like in matrices, the differentiation of beta naught, so you can search it in the Google. So the entire thing, this entire thing is the differentiation of this entire thing is 2x beta x x transpose into x beta transpose. The entire thing is written as this. Okay, so we need to equate this to 0, minus 2 y transpose x plus 2 x transpose x beta transpose equal to 0. Okay, so now we can get it as 2yx equal to, okay, 2 xi x transpose into x into beta I. So this cancel, and here it becomes beta transpose. We need to get beta, right? Beta transpose is known as y transpose x, okay, into x transpose into x inverse. Okay, this will go this side into denominator. We can't divide the matrices, right? So we need to use the inverse. Okay, we need to use the inverse. So for we need to get the beta, right? So I'm doing the entire transpose. Okay, so now beta will become beta equal to xi x transpose into x my inverse into whole transpose into xi x transpose. 1 minute, okay, let me clear it. Okay, so this is written as and into y transpose and x whole transpose. Okay, so now we can simplify it as beta is equal to x transpose x. Okay, suppose x, 1 minute, x transpose x whole transpose. Okay, so this thing, the transpose of the inverse is the same, right? The transpose of the a transpose a inverse of transpose is a inverse, right? So we'll be writing the same thing. Okay, so we'll be writing it as into beta x. This is the equation. So we'll be transforming it as beta equal to, okay, now x transpose into ex, x transpose into x whole transpose into x I y. Okay, so this is the beta. After the solving of the entire equation, we got to beta equal to x transpose x whole inverse into y transpose into x. Okay, so so we know that the matrix multiplication, the matrix inversing takes more time, right? Okay, to inverse a data, so to inverse a matrix, it takes around the complexity of n cube. So it takes more and more time complexity, so it requires more computation power. Okay, for implementing a multiple linear regression, when there are more number of features, then we need more computation power. So to eliminate this, we will be using gradient descent. We have discussed about open equations, like we will be using SGD. Okay, what is mean by SGD? It is a gradient descent algorithm which can be used for linear regression when the features are high. When there are many features, we will be using the gradient descent. All right, so okay, we use gradient descent because it takes more time complexity for inversing a large array. Okay, so let us implement this like using a small example. Implement this. So we can implement it. Let us suppose we have okay, area and price. Area, price, 1 2 3. Okay, area and price. Okay, this is area and price. 1 2 3, 300, 500, 700. So I'm taking a example. Okay, so I hope you will be calculating on your own. I will be directly calculating using the calculator here. Okay, so we know that for one example, one feature, the equation will be like y equal to beta naught plus beta 1 x. Okay, all right. So here the x is 1 minute. Here beta 1 x. So here x is x. 1 minute, the entire thing is going wrong. Okay, so here the x is 1 1 1 1 2 3, right? And y equal to 300, 500 and 700. Okay, 1 minute. Yeah, so this is x and y. Okay, so we write the input features in the matrix x with a column of ones for the bias term. Okay, for the bias term we'll be writing the first column as ones. Okay, so we need to implement this. So beta equal to x transpose x whole inverse x transpose, okay, the x transpose y. Okay, this we need to implement this. All right, so here let's implement this. X transpose y is implemented as 1 1 1. Okay, 1 1 1 and 1 2 3. 1 1 1 and 1 2 3 into 3000, 300, 500 and 700. So after calculating this we will be getting around, so this is 1500 and 3100. I hope you get the you know the matrix multiplication. So after this we'll be getting 1500, 3100 for x transpose y. Okay, so we need to calculate this also. Okay, now x inverse x whole inverse. Okay, this is implemented as 3 6 1 14 minus 1. Okay, so this is, so after calculating this we will be getting this. So this is written, this can be written as 1 by 6. So I'm just calculating. I have I have already calculated the entire thing, so I'm just showing you how we can implement it. So we have got the beta value, so where we can use the beta value in the multiple linear regression. So I'm just showing the how the mathematics works in the multiple linear regression. So we got this, and we need to multiply both the things. Okay, so beta equal to 1 by 6, 14, 6 minus 6 minus 6, 3. Okay, into 1500, 3100. Okay, we have calculated this. We have calculated the beta. So after we need to multiply this. Okay, after multiplying the beta values will be 400. Okay, 450. Okay, this is beta naught and this is beta 1. So the equation becomes y equal to 400. Okay, 400 plus 50x. 50x. So this is the equation we got. So let us substitute the formula here. Okay, so here for x is equal to 1. Okay, so for x is equal to 1, y will be y equal for x, 1 minute. So for x is equal to 1, x equal to 1, for x is equal to 1. Okay, for x equal to 1, y equal to 400 plus 50 into 1, that is 450. For x is equal to 2, x is equal to 2, 400 plus 100 equal to 500. Okay, oh, the pen is not working, the stylus is not working. This is 500. Okay, for x is equal to 3, for x is equal to 3, it becomes y equal to 400 plus 150, it becomes 650. Okay, we got 450, 500 and 650. Okay, so this is 550, 450, 500 and 550. I know that these are wrong because we have only got the list data, like we have only got the only 3 columns, right? So with the 3 columns we can't implement the model with more accuracy. So if you want more accuracy, we need to implement it with many more data points. Okay, so after using if we use many more, like after using around 1000 data points, then we can get an average plane where the values will be near. Okay, so this is how we can calculate the beta values in the multiple linear regression. I hope you understand this very well. And yeah, this is the mathematics behind this is the entire thing. Okay, if you want, just comment me, so I will, if you want this, I will upload a link. If you want this, just comment me. Yeah, that's it. This is the theory part. Let's see the coding part. Okay, let's see the coding part. It will be much more interesting.